All right, this is Physics 1A for, can't see the date, March 24th. Today we are going to be going through, I don't know what that was. I'm going to go full screen. F11, there we go. We're going to be solving this problem right here. This is a Newton's second law problem that involves a mass that's moving, well, two masses that are moving, and one of them has multiple accelerations that are not at right angles to each other. So this is a very specific type of problem. I want to make sure we cover the steps of how you kind of solve this type of thing. I'm going to move the chat down a little bit. I should probably make the chat a little smaller, but it's probably fine. Okay, so let's look at what's going on. It says, on the following diagram, all pulleys are perfect. All surfaces are frictionless. We want to find the acceleration A of the wedge. All right, so let's investigate what's going on here. So you have a wedge that has an angle up at the top right here that's 36.9 degrees. And at the bottom, you have wheels. So this wedge is basically free to move left and right. The wedge has a rope that's attached to the bottom down here. That same rope goes around some pulleys that are attached to the wall over here. Excuse me. And then comes back this way. And then it attaches to a mass right here. Now, this mass is in contact with the wedge. And so it's going to tend, and it's also free to slide. So this wedge is going to tend to slide down the ramp kind of in this direction here. Oh, I can't draw straight today. I need to do like this. The wedge is going to tend to slide down the ramp in that direction there, right? No, I'm sorry, the block will slide down the wedge in this direction here. And our goal is to find what is the acceleration of this wedge. So just looking at the problem, does it make sense to you all that that if this one moves, well, I'll just ask, if this box moves down the ramp, what's going to happen to the wedge? Yeah, it's going to slide to the wall, right? Okay. Now we're going to assume that the wedge doesn't tip over. Because to me, it kind of looks, when I look at it, at least, it kind of looks like there's a decent chance that this wedge might tip over. Like, for example, I don't know, if this mass was extremely heavy, I can imagine that the wedge might tip over. We're just going to assume that that does not happen in this problem. We don't have any information about how tall the wedge is or how wide it is. And so we kind of just have to assume that the wedge is not going to tip. Okay. All right. So in order to solve this problem, we're going to use Newton's second law. We're going to draw free body diagrams for both of the objects there. But before even doing that, I want to think about the accelerations that are happening in this problem. So we're given that the wedge is accelerating to the right with some acceleration that we're calling A, right? And so what we really want to do is to figure out what the acceleration of the block is going to be, right? So in order to do that, I want you to think about the following. I may need to draw a picture for this unless it's not super clear. If the block, right? If this block were to move down the ramp by, let's say, 2 feet. So let's say the block starts right here, and it moves down the ramp in this direction, obviously, and it moves 2 feet, let's say. How far would the wedge move? I want you all to kind of think about it. Okay, Kelvin says less than 2 feet. Andrew thinks it's exactly 2 feet. What do the rest of you think? Take some time to think about it. If you all want to kind of like open your mics and talk about it, you can too. If you don't feel comfortable doing that, you can kind of just write an answer down in the chat, whatever you think. You say it would be less because it's going down the steeper incline? No. Although that's a good idea. Okay, the cables, yeah, these cables are not elastic, that's right. You say you think it's 2 feet because the cable is not elastic and the length taken from the cable when it moves needs to be the same length as the wedge moves. Okay. Any other ideas? Does the number of pulleys determine how far the wedge moves? It's related to the number of pulleys, yeah. Maybe you could imagine what would happen if this whole thing... So, I mean, just there's a rope right here, right? It's one rope. It's attached to the bottom and it's attached to the top. So, I would say it's not so much the number of pulleys. Well, maybe it's related to the number of pulleys. But think about this rope right here. And what has to happen? If this one moves down 2 feet, where does that rope come from? If this one moves 2 feet, where does that rope have to come from? Where that cord have to come from? That question makes sense? From pulling from the bottom of the wedge. So you're saying from like basically down here? That's where all the rope's going to come from? So if this block moves down by 2 feet, you're saying that this cord on the bottom is going to get shorter by 2 feet? Is that what you're saying? Humbly says maybe because of inertia the wedge can move more than 2 feet. What would happen to this wedge if only the bottom chord got shorter? So you keep this constant. You're saying you keep this constant, but you're saying only the bottom chord gets shorter. What would happen to the wedge? No, not all the chords are the same length. There you go, Kelvin. That's right. So if this bottom chord was the only one to get shorter, then like it would have to tip over, right? Can you all see that? That if you only decrease this piece right here, then the bottom half of the wedge would move like to the right, while the top half would somehow have to stay still, and the wedge would tip over. Does that make sense to everyone? Okay. So that can't be the case, right? So I'm just going to ask again. If this little mass moves down by 2 feet, the cable has to come from somewhere, right? And we've just determined that it can't just come from the bottom. So where's it going to come from? Where's it going to come from? So maybe not only from the bottom, but the cable would come from the top and the bottom. Yeah, it has to, right? So as I said at the beginning, we were going to assume that this thing is not going to topple over, which, you know, maybe if you set this up in the real world, it would topple over. But we're going to assume that it doesn't topple over, okay? So in order for that to not happen, if the block goes down by 2 feet, then both the bottom cable and the top cable both have to get shorter. Can everyone see that? Does everyone understand that? I'm gonna draw a second picture here to show you why that's the case, but do we all agree that if this block is to move down by 2 feet, it is going to have to draw a cable from the top and from the bottom? Can everyone see that now? Okay. So what I'm going to do is I'm going to take this picture that I've been drawing over here on the right, and I'm just going to try to show you what it's going to look like when the block moves down, okay? So what I'll do is I'm going to... What's the best way to do this? We're going to copy-paste this picture, and we're just going to modify it a little bit. So what I'm going to do is I'm going to take the block, and I'm going to move it down. Oh, I didn't get the whole block, did I? Oops. I want to get this whole block here. Does that do it? Yeah, it does. Okay. So we're going to slide the block down, and I'll try to do this to scale as much as I can. So now I need to extend this rope, but I'm not allowed to extend this rope unless I also decrease the size of the other two ropes, right? What I want to do is I want to select everything except for the... I think that... No, it didn't work. It kind of worked, though. I think this is probably fine. So in order to make this work, I'm going to slide this direction, probably about that much. And now I'm going to shorten my ropes, like here. Oops. Now this is something I can't do in the classroom, so it's kind of nice we can do it in this picture. Oh, and I left off the pulleys need to be connected to the wall, right? So we'll do that right there. Okay, and then now we have to extend this one. So this would be basically kind of the before and after, so to speak, right? And you notice that when I did that, I had to shorten the top rope and I had to shorten the bottom rope, right? Now, how much did I have to shorten them by? Did I have to shorten them by the same amount? What do you think? Did I have to make both of them shorter by the same amount? Yeah, right? Okay. So now we know, okay, looks like this about the same amount each, so that distance of 2 feet is split by 2. That's exactly right. That's exactly right. So the answer to the question is, how far does the wedge move if the block slides 2 feet down the incline? If we have to split that distance in half between the top and the bottom, then the answer is that the wedge would move 1 foot to the right. Right? 1 foot. Okay, is everybody on board with that? Before we start getting into some of the mathematics of the problem? Anyone have any questions? Okay. So we know that... here, let me put this back up here. Ooh, lost the wall. All right. So now we have a pretty good I grabbed the ground from this one. So now we have a pretty good understanding about the relationship between how far the block moves and how far the wedge moves, right? So what I'm going to do is I'm going to say that if the wedge moves half as far as the block, right? The wedge moves half as far as the block, then I'm going to go back to my original picture here and say that if the wedge is moving with an acceleration of a, can anyone tell me what the acceleration of the block down the ramp should be? 2a, that's right. Okay, now we can actually start solving the problem. That's kind of the hardest part, maybe, I don't know. And I know for a fact that you have a homework problem that's similar to this on your Mastering Physics, because there's a question about it in the homework channel from someone. And it involves basically kind of a double pulley system where there is a very similar relationship where one acceleration is going to be a and one acceleration is going to be 2a. Okay, so now we want to start using Newton's laws, which means we need to draw free body diagrams for both of these objects. I don't like drawing the free body diagrams on the pictures, but we do have these two pictures over here. So maybe we could do that. Maybe that's okay. Let's start off by looking at the forces on the block. What forces are going to be acting on our block? Tension, weight, and normal. I believe that's correct. So there's going to be a normal force that goes this way. There's going to be a weight that goes straight down. Call this one mg. And then we're going to have a tension force that goes up this way. And these are definitely not to scale, so let's make this one a little bit shorter. There we go. Those are the forces acting on the block. And then what about the forces acting on the wedge? I think what we'll do is we'll draw the forces acting on the wedge over here, but then after we've drawn them, I'm going to make another free body diagram that's cleaner. So I'll draw the forces where they are on the wedge, and then, yeah. What are the forces on the wedge? Okay, weight, we can start with that one. Okay, so there's going to be a weight. I'll just draw it kind of from the center right here. It's going to be 4 mg.
Kelvin's saying there's going to be a normal force. Yeah, there's going to be normal forces from the ground, right? I'll just draw them as coming up from here. So half of the weight's going to be supported by this leg, and then the other half is going to be supported by this leg. We'll basically combine those into two. So what I'll do is I'll say that this is going to represent the normal force from the ground divided by 2. And this one over here will be the normal force from the ground also divided by 2. Okay, and we'll just combine those into one force. But each of they really probably wouldn't be divided in half, actually, okay? But there's going to be normal forces on both of these. So let's just say they're cut in half, and we'll make them into one force when we move to the next part. We're actually not going to need that force, as we're going to find out. Okay, what else do we have? 2t. Why are there 2 t's, Kelvin? Why not just 1t? Why do you say 2t? And you're right. Almost. Where's the second tension coming from? You're all welcome to talk too. You don't have to time. Would there be a second tension coming from the top? Yeah, top and bottom. Yeah, okay. You're both saying this. That's what's going on. Exactly. So there's going to be a tension in this cable that pulls the block to the right, and there's going to be a tension in the top cable too. So we're going to include both of those. So we'll say one tension goes this way, and then that same tension is going to be down here, going that way. They're both going to be a tension T. Anything else? No, Raina, it's 4mg because of the 4m right here. The normal force of the block, that's right, Tombui. So there's going to be a normal force coming from the block that's going to basically be like right here, for example. It's going to be the same force as this one right here, so I'm also going to call it N. That's the action-reaction force, right? You can see this starts to get really complicated when I draw it like this, but we will take all these forces and draw them just on a dot down here in a second. Sorry, I cut someone off. What was someone saying?
Oh, I was going to say that as well.
Oh, okay. Okay, anything else? There's actually one force that's missing now. This last force is probably not obvious. Any ideas?
All right, so when you have a pulley like this, right, and it has a rope on both sides, that rope is actually going to exert tension on both sides.
So there's actually another tension force, and you're going to see this show up in your homework too, on the lab manual homework.
That same tension force is also acting down like this way. Down at an angle like that. Because this block has weight, which is going to pull it down the ramp, and that's going to create tension in the cable, and that tension in the cable is going to pull on the pulley, but that pulley is attached to the wedge. So just like the tension goes to the right up here and to the right down here, you're also going to need a tension that's coming down this way. Does that make sense to everyone, or should I kind of try to explain more as to why that's true? I can give you a simple example as to why it's true if you want me to. Because this one is usually kind of confusing for people. The simplest way that I have to think about it is, imagine that I'm hanging a painting, okay? And I'm going to use a pulley to hang my painting up, okay? So I take a rope and I run it over the top of the pulley like this, and then I attach that rope to the painting here. So here I've got my painting down here, right? And at the top, it's basically held up by a rope that goes over a pulley that basically attaches here and here. Now, there's no doubt that you'd say that there's some kind of tension in this rope here. There'd be some kind of tension in this rope here, right? But you'd also have to have tension pulling down on the cable, on the pulley at the top, right? Like this. That's kind of what's going on. This is like, it's like these two cables are kind of hanging off of the pulley, basically. I don't know, does that help to help it to make sense? So now what I'm going to do is I'm going to take all these forces and we're going to put them onto just a free body diagram right here. We'll need a lot of room for this. Okay, so we've got our normal force. We're going to need the line that represents the plane. That right there. This was in. We're going to have two T's, so there's a T there. Straighten it up a little bit. Another T from up here. Okay, what I'll do is I'm actually just going to extend this one and make it 2T, because there's two of them. Okay, what else do we have? We've got our normal forces. Wait, copy, paste. There we go. And again, I'm just going to make that a little bit longer. Call that one the normal force from the ground. We also have this tension force that is going to point parallel to the inclined plane, like that. That's T. And did I get all of them? 3 T's, 1 normal force from the ground, normal force from the block, and 4 mg. So there we go. And then with these, we can just copy, paste, and just drag them down here. So we don't have to redraw everything. And we also need the inclined plane for this one too. We do not, however, need the block. Oops. Not that one. That one. Okay. There we go. Tension, normal, and this was the weight, right? Okay, so we've got our free body diagrams here. I'm going to separate them a little bit here. So on the left, we have the free body diagram for the cart. And on the right, we have the free body diagram for the wedge. We can also start to put some angles in here. So the angle at the top here is 36.9 degrees. I'm going to define that to be theta. So theta is going to be equal to 36.9 degrees. And that same angle theta should show up, it looks like, right here. And then on my picture on the right, it should show up right here. And I think from here we can kind of get to working. We do want to add in the fact that there's an acceleration because we're going to need to know that to do the problem. So on the picture on the right over here, I'll just say that the acceleration is going to be this way. And it's going to be A for the wedge. And for the cart, now I left something out. We know first of all, that the cart is going to be accelerating down the ramp with an acceleration of 2A. So we'll draw that on our picture here. So we know that it goes down the ramp with an acceleration that we can call 2A. But that 2A, there's a lot of different ways you can do this. So I'm going to show you maybe multiple ways of figuring this out. The 2A, basically, this represents the acceleration of the cart relative to the wedge, right? A represents the acceleration of the wedge relative to the Earth. So if I want to figure out the acceleration of the cart relative to the Earth, I need to add these two vectors together, and they're technically vectors. Okay? This 2A is down the ramp. And the A, the acceleration of the wedge relative to the Earth, is to the right. I technically have to add these two accelerations to each other. And they're not, like, in the same direction. The acceleration of the wedge relative to the Earth points to the right like that, and the acceleration of the cart relative to the wedge goes down the ramp like this.
So what I need to do is I need to vector add them. So what I need is I need another vector that points this way.
Because not only is the cart going to accelerate down the ramp this way, but it's also moving to the right, right? If you look at this picture first and this picture second, you can see that the cart moved down the ramp, obviously. It started here and now it's here. But what's probably not so obvious is it has also moved to the right by some distance. By the same distance that the wedge moved, basically, right? So we're going to need to add those two vectors together. Does that make sense?
Now, it may be easier to add them if we put them tip to tail, like this here. So I think that's what I'll do. We have A here and 2A right here. And one thing helpful about adding them tip to tail is I can add another line in here, like this. Make it black. I can add another line in here. We'll just make it go like that. And then one more to figure out some angles here. I'm going to add a line straight down like this.
And say that this is going to be our angle theta.
Which means that when I'm adding these two vectors together, okay, the angle doesn't, it's not obvious where that's going to show up. We have to use 90 minus theta, I guess, right here, don't we? How else got to get that same angle to show up? I guess if I went up this way.
Well, for now, I'm just going to say that I'm going to call this angle phi and say that phi is going to be the 90 minus theta. That's going to be 53.13. Oh, that's where it shows up.
If I draw one more line, and I make it perpendicular to that first line that I drew,
then this angle will be theta, right?
we could just do it that way. Because we need to add these accelerations together. So we'll do that. You know what? I don't need to make this so small. I can make this really large so you can really easily see what's going on. So those are our accelerations. Theta, theta. We need to break up A into components. One that points this way, which I'm going to make like purple. And then another one that points this way. A is the acceleration like that, and then we'll make this one, I don't know, what other colors do we have? Like dark blue?
Okay, so what would the length of this side be of this triangle here? If A is the acceleration along this direction, that's exactly right, Kelvin. So instead of just one direction, either x or y, it's combining both x and y to accelerate horizontally and vertically. Exactly. That's specifically what's so difficult about this problem, is that the block is not accelerating like in a simple, in a simple way. It's accelerating down the ramp and to the right. Okay, so if I tell you that this vector is A, what would the purple vector be? A times something, right? If this angle is theta. Cosine, right? Okay, so this side is going to be A times the cosine of theta. And then the other side is going to be A times the sine of theta.
Let me try to shrink some of these lines up a little bit here. We don't need them to be quite so long. Now, we're still just talking about the acceleration of the block here. All right, so here's what I'm going to do. I told you that you always want to pick your direction of your acceleration to be positive, right? And we can see that the block is basically accelerating downwards from this picture right here. But it's also accelerating kind of that way, up and to the right. So we're going to make our axes just like that. We're going to have this direction is going to be the positive, I don't know, we'll call this positive x direction. And the positive y direction will basically be up this way. And we'll be consistent with that on our picture, of course. This is going to be the positive y direction. And this will be the positive x direction. And that way, one of our accelerations is going to point this way. In fact, what I'm going to say over here is that our acceleration for the cart in the y direction is going to be a cos theta. And our acceleration for the cart in the x direction is going to be equal to 2a plus a sine theta. Okay, now we're done. We're basically done with the hard part now. So I'll just stop for a moment and see if I can answer any questions about what I've just done.
Professor?
Yep.
I think the reason why for the wedge for all the normal spaces, because as the wedge is being pulled in, which is tension, the block has its normal force of its direction. And the wheel's normal force because of its... I'm just saying as the wedge is getting pulled in, the wheels and the block are using its normal force, or however you say it.
The normal force of the wedge on the block is causing the block to move. Is that what you're saying?
Yeah, because I noticed as the
Yeah, that's right.
as the pulleys are causing tension, it's causing the normal force of the wheels of the wedge and the block to move.
You got it. That's right.
Because that makes sense.
Okay, good. Are there any questions at all about what I just said, though? About finding these two different accelerations for the cart? Like I said, you're going to have to do this in your homework problems. This almost this exact same thing is going to happen. It's not going to be the same calculation, but you're going to see problems where you have to do stuff like this. So, are there any questions about what I just did? Yeah. Okay, so let's go about solving this. So the steps for solving a Newton's second law problem are to draw your free body diagrams, draw your direction of acceleration, use that to define what x and y axes are. We've done that. And then the next step is to break up all the forces into components and then apply net force equals to mass time acceleration, right? So we're going to need to break all these forces up into components. Let's go about doing that. So coming over to our picture over here on the left, the force mg, we're going to have to break up into components. There's going to be one component that's going to go this way. That's going to be the y component. And then there's going to be an x component that's going to point down from here to here. Just making the components parallel. All of the rest of the forces are on an axis. So if this is mg and this is theta, this side over here I believe is going to be mg times the cosine of theta. And this side over here is going to be mg times the sine of theta. Coming over to our wedge, looks like we have a force T right here. So let's just be consistent here. Let's make the x direction, we're using, well, y direction, we're using purple. So the force T is going to have components. I'm going to draw them, I guess I'll draw them like this. So there's going to be a component that goes this way. And then there's going to be a component, oops, didn't need to do that. And then there's going to be a component that points that way. Make that one dark blue. Extend this line a little bit. Okay.
What are we doing it for MG again? I
What?
understand, but like, the components.
Over here on the left?
Yeah, I understand. It's just like, can you give me more explanation why not like the others?
Oh, because I'm making the y direction this way and the x direction this way, and the reason why I'm doing that is because the acceleration kind of makes it so that it's natural to make this the x direction.
Oh, okay, I understand. Thank you.
Okay, yeah, no problem. Okay, over here on this, we broke up the force t, so we're going to have components that are going to be... Let's see, this would be t times the cosine of theta, and the one on the bottom is going to be t times the sine of theta. Okay, we also need to break up the normal force n right here, so let's draw vectors for that one. So the normal force n is going to break up like this. There's going to be one component that goes this way, and then we'll have another component that goes down this way. And then n is actually, I'll move it so that it's like right here. If you look at the angles, this is theta, which means that this angle would have to be phi, 90 minus theta. And then this angle is also theta. So we'll put a theta right there. That means that this side over here is going to be n times the sine of theta. The side on the top is going to be n times the cosine of theta. On this picture in particular, I think I'm going to just use green to represent the x direction, because it's just really hard to see the difference between the colors. The blue and the... So there we go. N cos theta, n sine theta, t cos theta, t sine theta. And all the rest of the forces are just on an axis, right? So we're done with that.
Now all we need to do is to write down our force equations. So over here on the left, we're going to have, I guess we can use the x direction. We're using this color. We'll say net force in the x direction acting on our cart. So this is for the cart or the block or whatever you want to call it. Net force is equal to m times the acceleration in the x direction. And then we'll also have net force acting in the y direction is going to be equal to the mass times the acceleration in the y direction. I really wanted to make those a different color. That didn't work. I don't know why. Purple. We'll have those two equations. For the other guy over here, the wedge, we're going to have net force in the x direction is equal to the mass of the cart. And the mass of the cart is 4m times the acceleration in the x direction. And we'll also have net force in the y direction is equal to 4m times the acceleration in the y direction. Now, our wedge is going to just stay level as it moves across the surface, right? So what's the acceleration in the y direction going to be for the wedge? What's the acceleration in the y direction? We get 0, yeah, exactly. So that's 0. Okay. Let's go ahead and start filling in our equations from left to right. X direction is down the ramp. So going down the ramp, we have mg cos theta, which is going to be positive, minus t, which is going to be negative, and that's going to be equal to m times ax. Ax is this, so it's mass times, here, we'll write it like this, it's ma times 2 plus sine theta.
And I'm going to need to move this one over a little bit.
Now, okay, I skipped a step there, but I mean, if you look at this equation right here, you can say a sub x is basically just factoring a out of here. It's a times 2 plus sine theta. That's all I did right here. Okay, does this equation make sense? Does anyone have any questions about this? All right. In the y direction, we have n. We're making n positive because that's the direction of the acceleration. So we're going to have n minus mg sine theta and then ay we said was a cos theta.
Done with that equation.
Coming over to the wedge, in the x direction, what we have is 2t to the right plus t sine theta minus n cos theta is all equal to 4 times m. And then the acceleration in the x direction, going back to our original picture, remember that the acceleration of the cart was the one, that's what we're trying to find, or the wedge. The acceleration of the wedge is a, right? So it's 4ma right here. And we are now done with all the physics. The next 2 steps will involve math. So if any of these 3 equations do not make sense to you, let me know. I am not going to write this equation down because we do not need it. Please ask any questions if you have them, though. So these are our 3 unknowns. Tension, normal force, acceleration. The first equation has 2 of them. The second equation has 2 of them. And the third equation has 3 of them. So I hope you understand why I'm not writing down this 4th equation. We already have 3 equations with 3 unknowns.
So, Professor?
The 4th equation would only give us this. And we don't need that. What's up?
I have an idea for one of them. Do you see the f of y? I think we could do something about that.
What's that?
If for n minus y, ny sine of theta, I think we can move the sine of theta over to the right.
Are you talking about this equation right here?
Yes.
You want to move mg sine theta to the right-hand side?
Yeah, I was thinking of that, because if we do that, n on the left side will be by itself.
Okay. Yeah, so that's one way you could do this. You could solve this problem by solving for the normal force. You could plug the normal force in here. You could solve for the tension. You could plug the tension in here. That's not how we're going to solve it. But if you want to do that, you can. You're more than welcome to try that if you want. That should work just fine. Yeah.
Well, I just want to stay with the group.
Mm-hmm. Yeah. No, I mean, you're right. Absolutely. You can solve for the normal force right here. We could solve this one for the tension, right? And then we could plug them into this equation over here, and then we could do some algebra. And it would absolutely work, for sure. It would absolutely
But still,
work.
I want to do what you do, so no one gets mixed up.
No, just to be clear, that's a perfectly adequate way to solve the problem. I'm going to solve it in a different way that I think is less steps, but it's the same. It amounts to doing the exact same thing. We're going to use the elimination method to solve this problem.
This sounds good to me.
Okay, so
Everyone else in this room.
the thing that I notice when I look at these 3 equations are let me do one other step before I mention this. If we look at this first term right here, we have a tension in both of them. So what we can do is we can basically factor a tension out of the first 2 terms here. So we're going to do t times 2 plus sine theta. Okay, so this is what we're going to do. We're going to stack these equations together. We're going to multiply by some coefficients in order to get some things to cancel out, and we're going to try to solve this like that. So let's go about doing that. We'll start off with this one. Here, I don't want to completely erase these. Let's just copy paste. Oh, it didn't work. Copy, paste. There we go. Copy, paste. There we go. Okay.
Oh yeah, we're stacking them.
We're stacking them, right. Okay, now, if I want to add these 3 equations together, nothing is going to really get eliminated, unfortunately. Because if you look at the coefficient for t here, the coefficient is 2 plus sine theta, and that doesn't happen for this tension. This is just negative 1. And if I look at the coefficient for n, normal force, it has a cosine theta up here. But you all learn how to do this in your probably your first algebra classes, I would assume. So what we're going to do is we're going to say, okay, well, this expression, if I were to multiply the whole thing by cosine theta, and the bottom expression, if I were to multiply the whole thing times this, then I should be able to eliminate the other terms here. So we're going to, here, let me move this over to the right some. So my new expression is going to be, that one's not going to change. The second one, we'll just start writing this all out. The second expression here is going to be n times cos theta. Here, let me leave the colors the same so that it's clear where these things are coming from. So I'm multiplying the whole second expression by cosine theta. So it's n cos theta minus, we're going to have mg sine theta cos theta. Oh my god, I hate the way this works. Okay, there we go. Minus mg sine theta cos theta is equal to, cos theta times the right hand side is just going to be ma times cosine squared theta. The last equation down here, we're multiplying through by 2 plus sine theta. So the first term is going to be mg cos theta times 2 plus sine theta. Let's actually multiply it all out. So the first term is going to be 2mg, so 2 times mg cos theta. The second term is going to be mg cos theta sine theta. And then minus t times 2 plus sine theta. And all that's equal to, the right-hand side is ma times 2 plus sine theta times 2 plus sine theta. So that's 2 plus sine theta squared, which will be 2 times 2, which is 4, plus sine theta times sine theta, which is sine squared theta, plus the cross term. There's going to be a 2 sine theta and another 2 sine theta, so you're going to get 4 sine theta. I want to line up all the equal signs, so we're just going to shift this over a little bit so they're lined up. Just going back through what I did and why I did it. When we look at these three equations right here, I notice that this n is negative, but this n is positive, while this one has a cosine theta on it. So if I multiply this one by cos theta, they'll have exactly the same coefficients. One will be positive, one will be negative. For t, I notice that t here is multiplied by 2 plus sine theta, and the t down here is negative, but not multiplied by 2 plus sine theta. So, just like you learned in your algebra classes, we multiply by that coefficient. And now what we get is these equations. And all of these equations, if we stack add them, are going to give us our answer. So we're going to add these four equations. Ugh, so ugly. We're going to add all of these equations together. And when we do that, a lot of stuff is going to cancel. This whole term is going to cancel with this whole term here. The n cos theta will cancel with the n cos theta here. The negative mg sine theta cos theta is going to cancel with the positive mg sine theta cos theta here. The entire left-hand side of the equation cancels out except for one thing, which is... Oh my god, I'm sorry about that. I was blocking it. No one said anything, I was blocking it. Sorry about that. Here, so the part that was blocked out was the expansion of 2 plus sine theta times 2 plus sine theta, which was 2 times 2 is 4 sine squared, and then 4 sine theta. Okay, that was the only part that was blocked out. I'm really sorry about that. Anyway, all this stuff ends up canceling out due to the things that we multiplied by, and we're just left with that term right there. So what we have is 2mg cosine theta is equal to ma plus ma plus ma, so every single term has an ma in it, and it's multiplied by 4 plus cosine squared plus all of this and now we can simplify the right hand side, because you notice we have cosine squared plus sine squared. What's that equal to?
1. So we have 4 plus 4, which is 8, plus 1, which is 9, plus 4 sine theta is all equal to 2 mg cos theta. The masses cancel. Our goal was to find acceleration, and what we get is that the acceleration is equal to 2g cosine theta divided by 9 plus 4 sine theta. And that is the answer. We're going to plug in what theta is equal to get an answer that kind of makes more sense, but that's the answer. Since theta is equal to 36.9 degrees, I believe, if we calculate what what all that stuff is equal to, so we do 2 times cos 36.9, and then just divide by the denominator. What you end up getting is about a quarter of g. It's about 0.23 g. And if you multiply that by 9.8, you get about 2.22 meters per second squared. And that's the answer. We finished that in exactly an hour, even though we started a little late, and I gave you all, I hope, plenty of time to think about it.
Oh, Professor?
Yeah.
So when we multiply the left side by cosine of beta and 2 plus sine theta, weren't they based on the first equation that we saw, or we just guys,
I don't understand.
We had those 3 equations on the left.
These ones right here? Yeah.
Yeah, I was like, did we just multiply those 2 because of like they're in the first equation and they just might come in handy?
No. I know that this stuff can seem really complicated when I'm doing it with symbols, but what I'm doing is not as hard as you think it is. So suppose that I gave you the following 2 equations. I gave you the equation x minus y is equal to 5, and I give you another equation that is, I don't know, let's say 2x plus 5y is equal to 10. And I ask you to solve for x and y, right? So what we did is this. I said, oh, look, y is positive here, but it's negative here. What if I were to multiply the first equation by what? What would I need to... What?
Try 2.
No, I want to eliminate the y's. I want to
5. Oh, my bad. Try 5.
Yeah, so if I multiply by 5, then I'm going to get 5 times x plus 2x is 7x. 5 times y plus 5y is 0. And then 5 times 5 is 25 plus 10 is 35. So you end up getting x is equal to 5. And then y is equal to 10 or whatever. That's all we did. That's it. That's all we did. Right?
Oh, yeah, because...
So again, look at these 4 equations. We're trying to solve for acceleration. So we want to eliminate any variable that's not acceleration. And the way that I did it was basically to just say, oh, t times 2 plus sine theta here, negative t here. So what do I need to multiply the bottom equation by? I have to multiply by that. Negative n cos theta here, positive n right here. What do I need to multiply by? I need to multiply by cosine theta.
Oh.
In my opinion, this is a... I find this easier personally because I don't need to worry about like
the other ones.
Making a mistake in terms of like negative signs and positive signs when I move things around. The other thing is that like this will totally work out. You can solve it yourself if you want to by solving for the normal force and plugging in here, and then solving for the tension and plugging in here. So if you would prefer to do it the substitution method, please do.
I like the way you did.
Chase,
it's a lot
Chase,
faster and
stop.
easier.
Maybe. It doesn't matter though. I want to be 100% clear here. It does not matter how you solve these things. There are always more than one method to solve problems, right? And I want to encourage you all to use whatever method you personally want to use. You know what I mean? So yeah, it works out well, but I mean, and I will say on your homework, there are at least 2 problems where like this method of solving it will probably be faster, but I don't know. It's a good idea to have more than one way. You got a different answer, Kelvin? I could have made a mistake. Honestly, I really could have made a mistake somewhere. You mean when you plugged all the numbers in here? I think that answer is right, though. Yo, oh, that might be right. 1.37 might be right. What did I do wrong? So it's, we do 2 times the cosine of 37, or 36.9, right? And then we divide by 9 plus 4 times sine of 36.9. And we multiply that times 9.8. Oh, God, I got a completely different answer. Oh, I'm in radians. That's probably why I got a different answer. I must have just switched to radians, though.
Professor, I'm having some. Never mind.
Let's see, so if you do 2 times cosine of 36.9, divide by 9 plus 4 times sine of...
Yeah, I did get that. I mean, for grams, I got 0.14 grams.
Okay, you got it right. I got 1 point. You got 1.37? That's also what I got. I don't know what I did wrong the first time. So when I redo it, actually... My bad.
Oh, sorry.
What I got was...
0.14 G.
Yeah, what you just said, Chase, that's right. I got 0.14 G.
And yes, I multiplied by the acceleration, which was 9.81 meters per second squared, and it ended up becoming 1.37 meters per second squared.
Okay, thanks for catching that. I really appreciate that you all caught that. I can't even tell what I did wrong
we
the
both
first time.
caught that. I mean, some of us do.
I don't see what I did wrong. That's okay. Well, at least you all caught it. Okay, does anyone have any questions? I'm going to stop the recording here, but I'll be happy to stick around to answer other questions that people have. Otherwise, I hope you all have a good week.